Okay, so if you remember this classification or this hierarchy of oscillators, we have already covered the RC oscillators. And if you remember that, we said that the RC circuit can provide a low frequency, like relatively low frequency of oscillation from few hertz to maximum 100 kilohertz. And the LC, so if you'd like, this could work in an application like audio application, for example, like if you'd like to generate just whistles or something that's audible, you can just rely on the phase shift oscillator, wine bridge oscillator, and so on. But if you are working in high frequency ranges or applications like the RF circuits or RF stands for radio frequency applications, then you need to create an oscillator for like the local oscillator, for example, in a multiplexer or a modulator, right? If you'd like to generate a sinusoidal signal, a carrier in an RF circuit, then you might need megahertz, okay? So, or sometimes gigahertz.
Sorry to interrupt. Can't see your screen.
Oh, sorry. Oh, I didn't share the screen. Can you see the screen now?
Yeah. Yes.
Okay. So I was talking about, you know, the previous part when we presented the RC circuit oscillators. We said that these kind of oscillator, like the Venn bridge, you know, the phase shift oscillator, these oscillators could work in a low frequency application, like audio frequency application, like if you'd like to just create a sound, you know, like that's audible. So this is going to be within the hearing frequency range, which is 20 hertz to 20 kilohertz. So you can just use the RC circuits. That's fine. But in other applications like the radio frequency applications, like the local oscillator in a modulator or something, you might need higher frequencies, more than 100 kilohertz. So in this case, you have to use the LC circuits. Why the RC circuits are limited to this low frequency a little bit, relatively, it's because of the operational amplifier. So the operational amplifier has, remember, the maximum bandwidth, right? The bandwidth was, if you remember, for 741, was 1 megahertz or something. So you cannot go beyond this limit in the frequency oscillation. So if you need to have higher frequency oscillators, then you have to build it using transistors or other devices, or even a passive circuit without any active component, so that you can reach a range of 100 kilohertz to 100 megahertz or 1 gigahertz. If you need a very precise oscillator, you know, the oscillator that's used in wristwatches, you know, like precise clocks, you need to opt for something called crystal oscillators. Okay, so crystal oscillators are very precise, and they are made of crystals that gives you a vibration according to the frequency of the voltage applied. And this is a very precise frequency and could range from 10 kilohertz to 30 megahertz. Okay, so today we're going to, like in the previous lecture, we covered the RC circuits, and we studied two examples of it, the Venn bridge oscillator and the phase shift oscillator. Today we are going to study the LC circuit oscillators and the crystal oscillators, okay? And then we move to the non-sinusoidal oscillators after that, okay? So today's lecture outline is as follows. We will study first, we'll continue the sinusoidal oscillators, we'll study the LC tuned oscillators, then crystal oscillators. Then we move to the non-sinusoidal oscillators, what we call the multivibrators or relaxation oscillators. We will study the bistable multivibrators and the astable multivibrators. Okay, and as I mentioned before, the idea that's used in the sinusoidal oscillators depends on an amplifier and a tank circuit, or an amplifier and a filter in the feedback. And this filter has a resonance frequency or a peak frequency at omega naught, and you guarantee the oscillation when you have the loop feedback equals 1. Okay, but the non-sinusoidal oscillators depend on a different technique, which is charging and discharging of a capacitor. Okay, it's not far away from this one, because this one also you have kind of timing, you know, like charging and discharging, but this one is very obvious that you use a capacitor to charge and discharge. Okay, and at the end we'll study quickly a ready-made chip called the 555, and this is a very famous chip that I think you might use it in many applications and many projects. It's a very useful one that has, it's built in to work as a either a monostable multivibrator or as an astable multivibrator. So we'll study this quickly at the end. Okay, so as I mentioned before, if you need high frequency ranges like from 100 kilohertz to 100 megahertz, you need to opt for LC tuned oscillators. We will study two examples of the LC tuned oscillators, the Colpitts oscillator and the Hartley oscillator. And then we will study the crystal oscillator as a more precise type of oscillators, okay, of sinusoidal oscillators. So this is a general block diagram or circuit diagram of the Colpitts oscillator and the Hartley oscillator. You can see the difference only is that you switch it the C and L. You know, it's a tank circuit. You have a tank circuit here, consists of 2 capacitors and 1 inductor. In this case, you have 2 inductors and 1 capacitor. Okay, and of course you cannot see here the bias of this transistor, but it's there. You know, you have R1, R2, and a tank, another coil here. You know, and all the capacitors, the coupling capacitors and bypass capacitors are there. But just we simplify the circuit by just removing them because we are concerned about the AC equivalent circuit. So we just remove the biasing resistors and coupling capacitors and so on. So just to show you the equivalent, you know, the simple AC circuit. Okay, so let's study them one by one. So first we'll study the Colpitts oscillator. Okay, so the idea is to find the loop gain and equate this loop gain by 1 to 1, and then solve for the to find the resonance frequency or this frequency of oscillation and the gain required to maintain or to sustain this oscillation. Okay, so if you consider this Colpitts oscillator, where you have a transistor, bipolar junction transistor in the AC equivalent circuit. So basically there are some resistors here, but they are not shown in this circuit. And you have in the collector connected to a load R or a certain resistance R. This could be also the output resistance of the transistor parallel to the load, parallel to any other resistances seen from this side. And this is connected in this way to C1, C2, and L. So C1, C2, and L represent a tank circuit that will tune this circuit into to oscillate in a certain 1 frequency. Okay, and the goal now is to find how much is this frequency in terms of the capacitances and the inductance. Well, if you draw the equivalent circuit, okay, here we already omitted, you know, all the DC components, you know, the resistors and these things. The only step remaining, and also we short-circuited all the capacitors, the coupling capacitors. The only remaining part is to replace this transistor with its equivalent model. So AC equivalent model. So this is the AC equivalent model of the transistor. You need to notice here that we assumed, what's the missing part here in this circuit? In this equivalent circuit, there is a missing component. Can you tell me what's the missing component in this equivalent circuit? Is this the pi model of the transistor, or something is missing? So this is pi model, right?
Is it R naught?
Yes, R naught, but we assume R naught is infinity. Okay, so R naught is very big. Yes, that's part. Yes, but another essential part in the bipolar jet is this is bipolar junction transistor, right? It's not a MOSFET.
R pi?
That's correct. So we're supposed to have R pi here, right? So this is R pi. And again, also we assume that R pi is very, very large. So we assume it's infinity. Okay. So in this analysis, just for the sake of simplicity, we're going to assume both RO and R pi are infinity. Okay. So we are not going to use them. Okay. So let's analyze this one. We need to do KCL at this node here. Okay. How to do KCL here? How many currents we have? We have one current this way, and we have one current this way, one current this way, and one current this way. Okay, so we have 4 currents. Okay, so first of all, how much is the current here? Well, let's go this way, and we see that we need actually to define all the the currents here in terms of V pi. So V pi is our ultimate goal to find all the currents in terms of this voltage. Okay, so how much is this current in this branch here that goes this way in terms of V pi? Well, you see that V pi is the voltage across the capacitor here, right? V pi is the voltage across the capacitor. So if you divide V pi by, someone has a question? Okay. So can you join now, or? Anyway, I'm recording this this class or this lecture. So if you have any problem connecting with Zoom.
Yes, I was able to.
Oh, okay. Okay, that's fine. So I'm recording this lecture as well. Okay, so V pi divided by this impedance, okay, the impedance of this capacitor. You remember the impedance of a capacitor is 1 over j omega c, right? 2, okay, or 1 over SC2, right? So if you divide V pi by this impedance, you will get the current, okay? And this is what you get here. So this is the current through this branch here. So V pi divided by 1 over SC2 makes it SC2 times V pi. Now, how much is the current here? This current here is the same as this current here, right? It's Gm times V pi. So the next term is also a function of V pi. Now, how much is the current through these two components together? Because this current here plus this current is, we can consider it one current going through these two components at the same time. How to find the current through these two components together? They are in parallel, right? So all what we need is to divide the voltage here, VC, by the parallel combination of this one, right? The parallel combination of R and C1 is this one here, okay? It's 1 over this one. Like actually, this is 1 over the parallel combination. Now, how much is the voltage VC? Well, if you look at VC and V pi, you can say that V pi is a voltage divider of VC, right? V pi is the voltage from this point to the ground, is a voltage divider from VC. So VC times ZC2 divided by ZL plus ZC2, right? So V pi is VC times V pi is VC times I write it this way, ZC2 divided by ZC2 plus ZL, okay? And if you do this and solve for VC, you'll find VC equals this, okay? So VC is 1 plus S squared times LC2, okay? Then if you divide this by the parallel combination of this one, you're going to get this term. And you equate this with 0, right? Next, you just, since you have V pi in all the terms, and this equation equals 0, then you can cancel V pi from all terms, okay? So this one, you rearrange the terms, of course, then you get this equation here, okay? So you just put the s cubed in the beginning, then s squared, then s, then the free term, and rearrange the equation. This is what you get. Okay. Next, what you need to do is to, because we are looking for the frequency of oscillation, then we have to um, replace s with j omega to make this as a function of omega. So if you replace s with j omega in the previous equation, you will, and then you rearrange the equation to keep the real part in one side, in one side, and the imaginary part you isolate for them. Then you're gonna get this equation. Okay. Then since this equals 0, that means the real part equals 0 and the imaginary part also equals 0. Okay, if you have a complex number that equals 0, that means both the real part and the imaginary part are zeros. Now, if you go to the imaginary part, if you take this part and equate it with 0, you will have omega times C1 plus C2 minus omega cubed LC1 C2 equals 0, right? So that means if you divide by omega, this is going to cancel and this is going to be 2. Okay, so you have omega square LC1 C2 equals C1 plus C2. That means omega square equals C1 plus C2 over LC1 C2, which means that omega equals this. Okay, so omega, if you take the square root of both sides, you're going to have omega as square root of 1 over L times C equivalent. So this is the C equivalent. So C equivalent is C1 in series with C2. Okay, if you go back to the previous one, you find C1 and C2 are almost in series. So if you take C1 and C2 in series, this means, you know, series capacitances means C1 C2 over C1 plus C2. So this is just omega equals 1 over square root of L C equivalent. Okay, and we prefer to keep it this way because this is the resonance frequency. We know that the resonance frequency of any tank circuit is in the form of 1 over square root of L times C. The idea is to find L equivalent and C equivalent. Here L equivalent is just L, and C equivalent is this part here. Okay. At this frequency, if you now take this value omega and plug it in here with this omega, and take this part and equate it with 0, you are going to get this value for the gain. So the amplifier needs to have a gain. So this is the gain, right? So this is the gain. The gain of the transistor is GM times the resistance, the load resistance at the output. Okay, so the gain should be C2 over C1. So under these two conditions, this Colpitts oscillator will oscillate at this frequency, provided the gain is this much. Okay, any question? Okay, the same way we can do it for the Hartley oscillators. Now we're going to do the same thing for Hartley oscillator. Hartley oscillator is the same as Colpitts oscillator, except that you replace the inductances with the capacitance with the inductance, and the inductance with the capacitance. So you switch. Okay, so let's do the same thing, but I will do it here in a different way. Like I will use the same way we used before, which is to find A and to find B and to find A times B, the loop gain, and make the loop gain equals 1, and solve for the real part and imaginary part as we did before. Okay, so again, let's replace this with the equivalent circuit. Okay, and again, we should assume that R pi is infinity. So R pi is infinity, so we just ignore it, and we draw the circuit this way. Okay, so now we need to find AB, the loop gain, is VF over V pi. VF is here and V pi is here. Of course, VF and V pi are the same, But in this case, we're going to break the circuit here and assume V pi is different than VF. Okay, so we need to find VF in terms of V pi and then find VF over V pi. Okay, now to find VF as a function of VC, okay, we can say that VF is VC times, like there's a voltage divider, right? So I don't know if you can imagine this, because this is VC, right? And VF is the voltage divider of VC among the C and the L2, right? So I will show you this here. So you have VC here, and you have a capacitor, and you have an inductor to the ground, and you have VF here. Okay, can you see this circuit from this one? So VC connected to a capacitor, then you have VF, and this capacitor is C, and then VF is connected to the ground, because this is the ground and this is the ground, through a L2. So this is L2. So as you can see that VF is a voltage divider of VC among the impedance of this capacitor and the impedance of this inductor. So we can say that VF is VC times the impedance of the inductor divided by the total impedance, which is the impedance of the capacitor plus the impedance of the inductor. Okay. Now on the other side, how much is VC? VC is the voltage from this point to the ground, right? And we know before that the output voltage of the capacitor equals this current times the total impedance in the capacitor, right? And in the output. But again, the total impedance, you have to be careful. The total impedance is not just the impedance of R and L. No, you have to add this capacitor and this inductor as well. Okay, so you have this capacitor here and this inductor to the ground. And then this is infinity. So you have to take this and this in series, and the total impedance of these two, take it parallel to this, parallel to this. So this is the total impedance that you're going to multiply this current by. Okay, so we have to multiply the current gain, which is GM times pi, V pi, and negative because the current is going this way. And this is the total impedance. It's R parallel to SL, parallel to the impedance, parallel to this impedance plus this impedance, which is 1 over SC plus SL2. Okay, so this is the loop gain. Is it clear? Is this equation clear now, how we get to this equation of the loop gain? So again, we find VF as a function of VC. Okay, let me just delete this part here. Oh, let me delete everything. So we find first VF, this voltage, as a function of this voltage. And as I said, this is a voltage divider. Then we define VC as a function of V pi. So VC is this current times all the impedance seen by this current, which is this parallel to this series with this, okay, or with this. This is the same thing, you know, L2 is the same. We just put it here just for convenience to see that this is connected here. Okay, so this will lead us to this equation. Okay. Now we need to equate this with, because this is the loop gain, we need to make this equals 1, right? So this should be equal 1, and we take this one to the other side and make it 0, and then substitute S with j omega, and then separate the real part and the imaginary part, make the real part equal 0 and solve, imaginary part equals 0 and solve. If you do this, you're going to get omega equals square root of 1 over L1 plus L2C, and the gain should be GMR equals L1 over L2. Again, if you can see this is the same general form of 1 over square root of L equivalent times C. So always the frequency of oscillation in LC circuit takes you know, the value of 1 over square root of L times C. Here L is the series connection between L1 and L2, and C is the capacitor here. Okay, so these are the two conditions of oscillation to maintain or to sustain this oscillation of this Hartley oscillator. Okay, and by the way, you can use the same the previous one, the previous method as we did here. Just find do KCL here. Okay, you can do KCL here. Okay, the same way you can do KCL at this component at this point here and solve the equation. So, or you can do this here. You can use the voltage divider and find the loop gain and do the same way as we did it here. So you can use both methods in each circuit. Okay, now we found the two conditions for Colpitts oscillator and Hartley oscillator. Let's summarize this in one table. So the Colpitts oscillator has this circuit diagram. The Hartley oscillator has this circuit diagram. The frequency of oscillation for Colpitts oscillator is this one. For the Hartley is this one. And the gain GMR equals C2 over C1 here, and it equals L1 over L2 in this case. Okay, so this summarizes the two oscillators. Okay, let's have an example. We have an example here that uses Colpitts oscillator. Okay, we need to design a Colpitts oscillator given the following information. You have a bipolar junction transistor, and the bias current is 1 milliamperes, and the frequency of oscillation that need to be generated is omega 0 equals 10 to the power 6. And we have C1 equals 0.01 microfarad. Okay, and to calculate R, you have different parts. R consists of different parts. The first part is that you have to assume RO is not infinity in this example. So you have to use RO, and you remember that RO is here. Okay, and there is another load. Assume that you have a load resistance of 2 kilo ohms. You have also RL here is 2 kilo ohm. Plus, you always sometimes, you add a coil here in the tank circuit, and this coil has a resistance, and this resistance is defined by Q over omega naught C1. Okay, so R consists of three components: RO of the transistor, RL, okay, which is 2 kilo ohms, RO is 100 kilo ohms, and another resistance, which is the equivalent circuit of the inductor at resonance, which is Q over omega naught C1. So to find R, you have to add these three resistors in parallel, combine them in parallel. So that means R is R of the coil parallel to the RO of the transistor parallel to the load. And if you do this, having Q as mentioned here, Q is 100. We designed by Q 100, so this is 100. And omega naught is 10 to the power 6. And C1 is 0.01 microfarad. If you plug in these values here, you'll get this resistance. This resistance parallel to RO, parallel to RL gives you 1.64 kilo ohms. So now we found R. Okay. Now, how to find the gain, the transconductance of the gain, the GM? Well, as we know before, GM for a bipolar junction transistor is the collector current divided by V, the thermal voltage 25 millivolt. We know that the IC is 1 milliamperes, and we know that VT is 25 millivolt. If you divide them, you get GM. And remember, the gain is GM times R, which is calculated here. GM times R equals C2 over C1. We now know GM, we know R, we know C1. From this, we can calculate C2 as this. Okay, so it's going to be 0.66 microfarad. So we found the other component C2. Okay, now we know this one. We need just to find L. How to find L? We use the frequency of oscillation formula, okay, which is square root of C1 plus C2 over L times C1 C2. From this, we can solve for L, and L becomes 101.5 microhenry. Okay, so it's just a straightforward application of the two conditions of oscillation. Okay, so you know some parameters and you find the other one. So as I mentioned before, most of the questions either to design the circuit by finding the components R, C, and so L, and so on, or analysis questions when I gave you RC and L and I asked you to find the frequency of oscillation, the gain required for the oscillation, and so on. Okay. Any question? Okay. Now we move to the third type of oscillators, which are the crystal oscillators. Crystals like quartz and other, substances in nature are found in nature, and these are kind of material or substances that have an amazing phenomenon. Okay, if you have a piece of a crystal material or substance with a thickness T, okay, and you shape it in a slab like this or in a piece like this, and you connect a piece of metal here and a piece of metal on the other side, and you connect this to a voltage source, an AC source, with a frequency F, okay. Then this, and you apply this voltage across this crystal. So this is a crystal. We call it sometimes piezoelectric material. The piezoelectric material has this phenomenon of if you apply a voltage across it, it will vibrate with the same frequency of the input. And this vibration will have a resonance peak. So it's maximized at a certain frequency F node. So it's like a tank circuit. So we can consider this as a filter. Okay. So it will resonate in all frequencies, but the highest oscillation frequency will be at F node, and this F node is roughly K divided by T. T is the thickness, and K is a constant. So the frequency, the resonance frequency of oscillation is proportional to the thickness. Okay. So the bigger the thickness, the smaller the resonance frequency. The smaller the thickness, the higher the resonance frequency. Okay. So this is, and by the way, the crystal works in both directions. So if you apply a voltage, it will vibrate. And the other, the other side works too. If you vibrate this crystal, it will generate a voltage. Okay. So, and this frequency is very precise. Okay. The frequency of oscillation here, the resonance frequency, is very precise. And it, by the way, it happens at multiple of frequencies. So, like F node and 2F node, 3F node. So it has multi-tones, the fundamental frequency, it oscillates at the fundamental frequency and the multi-tones of it. So you can use this also to generate not only the frequency of resonance, but also multiple of this one. So if the frequency of resonance is 1 megahertz, then you will have an oscillation at 2 megahertz, at 3 megahertz, 4 megahertz, the harmonics of that. Okay. So we can utilize this quartz, and as I said, this frequency of oscillation is very precise. This is why this crystal oscillator is used in precise, applications that needs precise clock or precise oscillation, like wristwatches and some, clocks, very precise clocks that we need oscillators. So of course we generate some oscillation, and then we divide it until we get the 1 second, and then divide it to get 1 minute, and from the minute we get 1 hour, and so on. The equivalent circuit of a crystal oscillator is similar to a tank circuit. So you already have the L, C, and everything. So R is very small. R, you can consider it as a 0. It's very small. And you have L, and you have a series capacitor and parallel capacitor. So CS is series to L, and CP is parallel to it. Okay. So in above resonance frequency and below resonance frequency, the dominant component is CP. Okay. But within the resonance frequency, within this range here, this range of frequency, the dominant is the inductance L. So this crystal around the resonance frequency is an inductive. So it's similar to having an L, okay? So we can use this in a Colbit's oscillator, and we replace the coil of the Colbit's oscillator by the crystal, okay? So it will make a tank circuit that resonates at a frequency relevant to the inductance L, okay? And if you'd like to find, but the proof here is not important, if you'd like to find the frequency of oscillation, is going to be given by this formula here. So it's omega equals 1 over square root of L times C. Remember that we always say that the frequency in the LC circuits is given by 1 over square root of L times C. In this case, L is the equivalent inductance of the crystal, and CS is the series capacitor of the crystal itself, okay? So this is about all about the crystal oscillators, okay? Do you have any questions? So now we finished the sinusoidal oscillators, okay? So this is the first category of circuits that generate sine waves, sinusoidal waveform. Now we move to a non-sinusoidal oscillator. Do you have any questions for the previous part? Okay, so if you remember, let me just show you the here. We said that we're going to study the sinusoidal oscillators, and these have RC circuits, LC circuit, and crystal oscillators. Now we covered all these three parts quickly, like briefly, and now we're going to move to this side for the non-sinusoidal oscillator. These circuits produce waveforms that's not sine wave. There might be square wave, triangular waveforms, rectangular waveforms, and so on. Okay, so we are going to move to the second category or second class of oscillators. Okay, as I mentioned before, we have three types of multivibrators. So this family of oscillators, the non-sinusoidal oscillators, are called multivibrators. We have bistable, monostable, and astable. Bistable means you have two levels. You can toggle like flip-flop. You can switch the output to be either high or low. So between these two levels. Monostable is just one level, and momentarily you can switch to another level and go back to the previous level. As I mentioned before, like the doorbell button, like the doorbell button, when it's all the time is in the 0 state, right? Once just you press it and release it, it's gonna go momentarily to the on state and then go back to the off state again. So this is what we call monostable. It just has one stable state, and it can go to the other state for a short period of time and then comes back to the stable state. Okay, but this one you can switch it to either one of these two states, either high or low. Okay, so this is why we call it bistable. So it has two stable states, and this one has only one stable state, which is, let's say, the low. But sometimes you can move it to the high state for a short period of time, and then it will come back by itself to the low state. So it loves to stay in the low state all the time. So this is why we call it monostable. The astable is a device that will generate output that will swing forever between the low state and the high state. Okay, so this is the difference between the three multivibrators. Of course, these are not like continuous oscillators, the first two ones, but we add them to the category. Okay, so let's first study the bistable, and then we'll study the astable. Okay, so bistable could be designed using an op-amp like this. So what's weird about this op-amp? Is it the same negative feedback operational amplifier that we used to do, or has something weird?
Looks like it has no input. Both
Yes.
sides are grounded.
Yes, this is the first one. We have no input, or we have no input if you assume it here. Okay, second. How about the feedback? So the feedback is positive, right? We don't have a negative feedback. You remember our original negative feedback? Always we have to have this feedback to the negative terminal, not to the positive one. We have this as ground, and then you have the input here. So this is negative feedback, R2 and R1. So this negative feedback. But this one is positive feedback. Okay, so always when you need to have an oscillator or a comparator, you use a positive feedback. Okay, so positive feedback. And remember, in the filters and feedback circuits that we studied negative feedback. But in this case, since we are generating oscillators, we need the output to alternate between the maximum and the minimum to saturate either to the positive saturation level or to the negative saturation level. So we have to use a positive feedback. Okay, so and how much is V plus? Okay, if you have V out and you have this feedback, how much is V plus?
It's the voltage divider.
That's correct. Voltage divider of the output. So V output times R2, R1 over R1 plus R2. Okay, which is beta, is the feedback factor. Remember beta from the feedback times V out, where beta is R1 over R1 plus R2. Okay. Now, as you mentioned, there is no input here. So let's study this case. What's going to happen? What do you think is going to happen if you don't have any input? Well, someone would say if the input is 0, then the output is 0, and the feedback makes, voltage divider. So this is also 0, and we are happy because the V plus and V minus are all zeros, so everything is stable. No, this is not going to happen. Why? Because even if you connect this to the ground, due to the circuits and capacitors, transistors and components inside, these circuits or these components might generate some amount of noise. So you will have some amount of noise here. Okay, so that this terminal will go slightly higher. Assume that the voltage here, V minus, becomes 0.000001. It's very small voltage, due to any internal noise. Okay, what do you think is going to happen? Now remember, this was 0. And this voltage is sorry, I'm not. I don't mean V minus. I mean V plus. Sorry, this voltage here has a certain V plus got higher than the ground. Okay, for some reason, because it's not connected to the ground, V plus is not connected to the ground, and for some internal noise, this amount is just above the 0 by a very small amount. Okay, well, remember that the operational amplifier has a loop gain, an open loop gain, open loop that's almost infinity, right? It's very high. So this very small amount of input at V plus, remember the output is going to be A open loop times V plus minus V minus, right? V minus is 0, is connected to the 0. And V plus now is having this 0.000001. So this will give you a certain voltage. Okay, let's say 10 volt or like V1. Okay. So now this very small amount of noise will generate a voltage at the output. This voltage will be fed back to this one. And let's assume this is 10 volt. Then you will not have here 0.00001. You will have 10 volts times R1 divided by R1 plus R2. So this is going to go up from this. Let's assume that this is, and we have to have also a high gain. This gain is not 1. R2 is not the same as R1, or the gain here is not, the beta is not 1. Okay, so assume that R1 is smaller than R2, and this is 1, and this is 10. So you have a gain here of almost, let's assume this is 9, right? So to make it 10, gain of 10, so let's assume this is 9, right? So V plus, as we mentioned, is gonna be R1 over R1 plus R2 times V out. And in this case, you will have a voltage here, okay? So you have a voltage here, which is how much? So 1 over 10 of V1. So the voltage increases, okay? So the voltage got increases, okay? From this one to maybe 1 volt or something. And then you keep increasing this volt, because this volt will be amplified again to get V1 is higher, and then feedback again to increase. So this will keep increasing the voltage higher and higher and higher, okay? Higher and higher and higher, okay? So what's gonna happen? Can you keep increasing V out until you reach infinity? Does it mean that V out, because of the positive feedback, will keep increasing to infinity? Or something is gonna happen?
It'll reach a limit because of VEE and VCC.
That's correct. So assume that you have a voltage source here, VCC, and a negative voltage here, VEE. So this will hit, you know, and it will keep growing until it hits the saturation limit. The saturation limit not necessary to be VCC, by the way, you know, like ideally it's VCC, but practically it's less than VCC because you have inside here some transistors. So you have to consider the VCE sat, and you know, so if this is VCC is 10 volts, this might be 9 volt or 9.5 or something. So it's not necessary to be exactly the maximum, but ideally it is the maximum. So even if you have a connection like this without any input, due to the internal noises, this will, it depends. If the noise is positive, this will hit the maximum. Now, if you repeat the same thing with a negative voltage, so if this is negative, then everything will be the same except that you will hit the minus VE or the negative rail. Okay. So even if you build a circuit like this using an operational amplifier with a positive feedback, you cannot predict the output. The output might hit the maximum or the minimum. It's something random, you know. You don't know. Like depends on the built up noise at the positive term. Okay. So this is considered a bistable thing. So this is just the basic idea. Okay. I'm going to show you an analogy here. So this is similar to having this ball on this tip here. Okay. Can you sustain this ball here on the tip forever? Practically, no. Why? Because if you put it here, due to some wind, some dust here, some anything that will affect it from outside, it will either go this way or this way. So this way is the upper level. We call it L plus, the maximum saturation level, which is almost VCC, and this one is L minus, which is the negative saturation level, which is close to the VE. So this is a nice analogy for the bistable circuit. If you keep this ball here, you cannot keep it. It's difficult, like ideally, you cannot leave it here forever. Okay. Okay. Now let's see how to use this in a useful circuit. Okay. Okay. Now we have removed the ground from the negative terminal, and we applied a certain voltage. Okay, so we assume that V input here, V negative is V input. Now, how to find the output with respect to the input here? Like we need to find the output input characteristic. We need to find V out as a function of Vn, knowing that beta is R1 over R1 plus R2. Well, now this input compared to this input gives you the output. So let's assume that the output is at L plus. Okay, in all these bistable or astable circuits, you have to start with assumption of the output, because you don't know, like randomly the output might be at L plus or at L minus. Okay, so now let's assume it's at L plus. Okay, and whatever, L plus might be 10 volts, 12 volts, 15 volts, whatever. Okay, so in this case, how much is V plus? Well, don't forget that V plus equals R1 over R2 plus R1, or R1 plus R2 times V out. So it's a fraction of V out. So if this is 10 volt, this might be 1 volt, 2 volts, something positive. So this is going to be positive, right? Positive value, but less than L plus, right? So this value here is beta times V out, okay? And since V out is L plus, then this is going to be beta L plus, right? Okay, now let's start V input from 0, okay? So if V input is less than V plus, then the output is still high, right? So think of this as a comparator. You know, this operation amplifier compares this voltage to this voltage. If this one is higher than this one, the output is V plus. I mean L plus, which is the highest saturation level. If V minus is higher than V plus, then the output is the minimum or the lower saturation level, which is L minus, right? So now we said that this one is how much? This is beta L plus, right? Why? Because this is V plus, and V plus is a fraction of V out, and we assume that, so this is assume in the beginning that V out is L plus. So L plus got feedback here, so V plus is beta times L plus, right? Now, if V input is less than BL plus, which is V plus, then the output will stay at the highest level. When does the output switch from this level to this level? When this input voltage becomes higher than this voltage. So the output is at VL plus. Once the input is less than this value here, you stay at this level. Once the input switches from less than BL plus to beta L plus to beyond or above beta L plus, which is the VTH here, we call it V trigger. So VT, T means trigger, and H means high, and L means low, okay? So once the input voltage go above the V trigger high, which is BL plus, then the output will all of a sudden switch from L plus to L minus, because now there's a negative terminal has a higher voltage than the positive terminal. Okay, now let's assume the other way around. Okay, so I'll delete everything here, and let's go back from the negative assumption. So let's assume now that this one is L minus. How much is the voltage here? V plus will be beta L minus, right? And now this one is higher than this one. Okay, assume that this one is bigger than, V input is bigger than, and we are in this side here. So V input is bigger than beta L minus, which is here. Why is it here? Because beta is less than 1. Beta is a fraction of 1, like it's a fraction, it's less than 1. And L minus is negative. L minus is relevant to VEE, right? So, and VEE is negative and VCC is positive. L plus is close to the VCC, and L minus is very close to the VEE, which is negative. So this value is negative. You have here minus 2 volts or 3 volts or whatever. Okay, so if this is higher than minus 2 volts, like 4 volt, 3 volt, 2 volt, 0, minus 1, greater than minus 2, you will sustain the minus level at the output, the minus saturation level at the output. But once this one goes below this level, which is BL minus, then the output will go to the transition and move from the L minus to the L plus. So in the going way, you go this way. When you go back, you don't trace the same, you don't go back like this. Oops, sorry. On your way back, you don't trace the same, or you don't go to the same trace again. You don't go this way. No, in the way back, you go this way. So In the forward direction, you go this way. In the backward direction, you go this way. So this is the overall transfer function or characteristic function, okay? And this part here, we call it hysteresis. So you have a comparator with a hysteresis, okay?
I have a question.
Yes.
Okay. How does L plus and L minus affect the feedback when they are equal?
Sorry, can you say that again?
You know, what happens to when L plus and L minus is equal? How does it affect the feedback?
L minus and L plus are equal?
Yes. What
No,
happens?
L1 and L minus and L plus cannot be equal. L minus is the maximum value of the minimum value of the output, and L plus is the maximum level of the output. These are not, no, the output might take either one of these levels, but you cannot take them at the same time. The output could not be L minus and L plus at the same time. Okay, let's assume L plus, assume it's the same as VCC. And we'll assume this as a minus VEE, okay? So this is say 10 volt and this is minus 10 volt. So the output will switch between 10 and minus 10. So for these circuits, when you have a positive feedback, the output is always saturated. It cannot be in between. You know, the output cannot take any number, any value between these two, either this or this. That's it. It's not an amplifier. So the output is not 5 volt, 2 volt, no, cannot take any of these values. It's either 10 volt or minus 10 volt. That's it. Or 5 volt minus 5 or 9 minus 9. So what do you think of the output in this situation? Well, if V minus is bigger than V plus, then the output is L minus. If V plus is bigger than, this is the idea, if V plus is bigger than V minus, then the output is positive VL. Okay, let me give you a question and see if you understand this. Okay, if I draw this circuit, can you tell me how to draw the characteristic? I don't have a feedback here. So the output also goes to either L plus or L minus, right? Because this is a comparator, there is no feedback. So the output will look, is V plus greater than V minus, then it will take the highest level. If V minus is greater than V plus, it will take the lowest level, right? So what would be the characteristic curve for this circuit here? Can someone tell me? Like let's plot the axes like this, right? And this is V input, which is this one here. And this is V out. And assume Vn is negative. We are here. If Vn is negative, how much is V out?
Still negative.
Yeah, it will be L minus, right? Why? Because this one is negative. This one is 0, right? The negative terminal V minus is 0. Now V plus, let's say it's minus 2. Now the output will look, which one is higher, the negative or the positive, V plus or V minus? It will see that V plus is lower than V minus. So V minus is higher. So the output will saturate at L minus. Okay? And this will go all the way until you reach here. Once V plus switches from the negative to positive, then the output will also switch from L minus to L plus. And this is the characteristic curve. Here you have no hysteresis, because if you go back, if you reduce V input from the positive to negative, then the curve will go this way. So the curve could go this way or this way. Okay, on the forward direction, you go this way. On the reverse direction, you go on the same curve. But in this circuit here, you have hysteresis in between. You don't go on that same trace twice. You know, if you go from the negative to the positive, you go this way. If you go from the positive to the negative, you go this way, or from the high to low, or low to high. Okay. Okay. So now let's do the other way. Like this is an inverting input, right? The input is a negative. Is applied to the negative here, right? Let's apply the input to the positive and see what's going to happen. Okay, let's analyze this circuit. Okay. Well, here you connect this to the ground, which means that V minus is always 0 volt. Now, what's going to happen if you keep changing this one? Well, let's assume that this one at L minus. Okay, and this one is negative. Okay, so if this one is negative, why is this one? How much is the voltage here? How to find the voltage at V plus? Well, to find the voltage at V plus, let's do the superposition. Okay, superposition. Sorry. So if you assume that V out is 0 and you find the V plus due to the V input, so this is what you're going to get. So due to V input only, the V plus is V input times, because you assume this is 0. So V plus due to V input only is V plus V input times R2 divided by R1 plus R2. Now, you assume that this one is 0. And you find V plus due to V output only. So in this case, if this is 0, then V plus is V output times R1 divided by R1 plus R2. Then you add them together, because the superposition, you have to add the two outputs. You add them together, you get V plus. Okay. Now, when the transition happens, the transition happens when, like, you can assume that V output is either V plus, L plus, so V out is either L plus or L minus, right? So let's assume we are in L plus. Okay, so V out is L plus. So this is V plus equals V input times R2 over R1 plus R2 plus L plus times R1 divided by R1 plus R2, right? Now, the transition is going to happen when V plus crosses the 0. Okay, so if we switch, or if we substitute this one with 0, this is gonna give you the V input at the threshold, at the high threshold. Okay, sorry, at the low threshold. Okay, so if you substitute V plus with 0 and solve for V input here, so V input will, so if you substitute this with 0, you can just delete this one and delete this one, and you will have 0 equals V input times R2 plus L plus times R1. If you solve for V input here, you're going to have V input equals L plus, negative L plus times R1 over R2. And this is at the threshold when you switch from the, you know, the positive to negative, or the negative to positive, and this is V threshold, or sorry, the V threshold or V trigger low. Okay, so to find V trigger low, you just substitute V out with L plus and solve for V input. Okay, and the other way around, if you'd like to find the V trigger high or threshold high, you have to solve, to substitute V out with L minus and solve for VI and call it V trigger high. Okay, so basically what happens is that you will have the same hysteresis loop, but in flipped, you know, the other way. If you go back to the previous one, you can see this one goes this way and comes back this way. This one goes this way and comes back this way. Someone has a question? Yes?
Yes. I'm not quite sure I understand what happened to the bottom terms of the V plus expression.
You mean these ones?
Yes, after substituting V plus as 0, I'm not sure what happened to the denominators of the other term of the VI and V out terms.
Okay, so let's plug in here V out with L plus. You agree with this?
Yes.
So this means equals, okay, VI at, this is at threshold, okay, at threshold.
Yes.
So at threshold, V out equals V, the highest value, which is L, right? L plus, right? Okay, so let's substitute V out with L plus. So this is Vn times R2 over R1 plus R2, right? Plus L plus times R1 over R1 plus R2. You agree with this?
Yes.
And we make this at the transition, V plus has to be 0, right?
Correct.
Okay, so if you substitute V plus with 0, you have these two terms added equals 0, right?
Correct.
Okay, multiply by R1 plus R2, both sides. So if you multiply this term by R1 plus R2, this will cancel. If you multiply this term by R1 plus R2, this will cancel. If you multiply 0 by R1 plus R2, this is 0.
Oh, okay, okay, okay.
So this means VI R2 equal plus L plus R1 equals 0. You agree?
Okay, okay.
Rearrange this, you will get this one. But this is not at any V input, at the V input when it crosses the threshold or the trigger. So at V input at this point here, when you are going from this way to this way.
Okay.
Okay, and you do the same thing for the L minus, you get this equation. If you substitute V out with L minus and solve, you're going to get the other threshold. So the threshold here, or the trigger values, are the same as the one before, except that, you know, the curve is flipped. You know, instead of going from this way and switching like here, you know, you do it the other way around. Okay, so from the negative and positive is the same, except that, you know, the values of the threshold or the trigger is different. Here the value of the threshold, high and low, are these values: beta times L plus, beta times L minus. And how much is beta? Is R1 over R1 plus R2. Here it's the same thing, but flipped. You know, you just flip the curve vertically like this. The second thing, V threshold low and V threshold high are not given by beta, which is R1 plus over R1 plus R2 times the L. No, it's given by this. So you can assume this is beta in this case. Beta is different. It's not R1 over R1 plus R2. It's R1 over R2. That's it. Okay. So the threshold level here are different, and the curve itself is flipped. Okay. So this is if you use the non-inverting terminal compared to the case when you use the inverting terminal to apply the input. Okay. So generally we can do this in many different ways. This is a comparator without hysteresis, and this is a comparator with the hysteresis. And we can also shift the hysteresis to a certain reference voltage. How to do this? We do this, instead of applying a 0 voltage here, we can put a reference. If you put 1 volt here, this curve here, or this hysteresis loop, will be shifted to the right by 1. If you put 2 volts here, you will shift it 2 instead of having 0, because the transition happens. Why did we substitute V plus with 0 here? Because the transition happened exactly at the moment when V plus crosses this voltage here. So if this voltage is 0, once V plus crosses the 0, the output will switch, whether in this way or in this way, in this direction or in this direction. So now if we do the same thing, but we substitute or replace, you know, instead of having a ground here, so this is the circuit here, how to implement this circuit. You do like this, you do the positive feedback. Okay. And you apply the input here. And this is R1, this is R2. And the inverter here, the inverted terminal, instead of connecting to the ground, we will connect it to V reference. Okay. If you do this, you shift the hysteresis loop to the right by VR. Now this is the one with hysteresis. This one is without hysteresis. Can someone tell me how to do this, how to implement this? There is no hysteresis here. You go this way in your forward direction, and in the backward direction, you go this way on the same line. How to implement this one? What's the circuit? You know, this is the block diagram. How to do it, the circuit like this one.
I guess when there's no R1 and R2.
Exactly. So this is V out, no feedback at all. You make it a pure comparator. Sorry, this should be the negative and this should be the positive. And instead of connecting this to the ground, you connect it to V reference and the input here. Okay. So now the comparator works as follows. When this plus is higher than minus, then the output will go to L plus. When this inverting terminal is higher than the non-inverting terminal, the output will go to L minus. Now this is maybe V reference as 2 volts, for example. Okay. So if VI is negative or 1 volt or 0 volt or 1.5 or 1.99999, all these values, still the inverting terminal is higher than the non-inverting. So the output will be negative. Once the input goes beyond this reference, so this is the input, right? So this is here 1.9999. Once the input goes beyond 1.92, above 2, the output will switch from the negative to the positive. So for all the bistable and astable, S-stable, the output takes just 2 levels, plus or minus. The positive saturation level, you can say ideally VCC, or the minimum saturation level or the lowest saturation level, which is ideally VEE, which is negative. Okay. So we can shift, this is the goal of this slide, is to say that we can shift this to the right or to the left by adding a reference voltage instead of connecting this to the ground. Whether if you have a comparator or a Schmitt trigger. By the way, this comparator, this is a comparator, a regular comparator. And this is a Schmitt trigger. We call it Schmitt trigger, as we're going to see in the next slide, I believe. So this is called a Schmitt trigger. Okay. It's not mentioned here. Okay, let me just write it here. So this case, this is a comparator. If you have a comparator with hysteresis, we call it Schmitt trigger. Okay, and Schmitt is the name of a person. Okay, so let's see how to use this, what application we can use this. Is this comparator better than this one in the applications of bistable or not? Okay, well, let me show you here. Okay, assume you are using this comparator to control the temperature of your room. So one application is to use this as a controller to your temperature, room temperature. Okay, meaning that you have a thermostat that detects the the temperature, and take this thermostat and convert the temperature into voltage, and you apply this voltage here. And in the reference, you have certain DC constant, like 2 volt. In low temperature, the input here is lower than 2 volt. Once the temperature goes high, this sensor will detect the temperature, convert it to a volt, and this volt might be higher than 2 volt. In this case, you will switch the output into on state. Before, if this is lower than this, the output is low. So you don't trigger the air condition. Once the temperature of your room gets higher, the voltage here will go up and becomes above. Once it becomes above 2 volts, then the comparator will trigger the output and say, okay, go from low to high. And this high will control the air condition to start turning on. Once the air condition is on, it will cool down the room. It will cool down the temperature. So this is a feedback. It will cool down the temperature of the room, and then this will go down. This is the same thing, but the direction of going forward is different than the direction of going backward. What do you think? Which one do you think is better, this one or this one? VR here is corresponding to the room temperature that you would like to set, the set point, okay? So VR corresponds to temperature of, let's say, I'm used to the Celsius. So I don't know how Fahrenheit is 70. Let's say 70 degrees Fahrenheit, okay? So you set your temperature thermostat at 70 degrees Fahrenheit. Oh, what time is it now? Are we over time? Oh. Okay, so if you set this one here and at the temperature of this T 70 Fahrenheit, what's going to happen if you go beyond this temperature, the actuator here the output will go high and the AC will work, right? Once the AC works, the temperature will go down. Once it goes down, you will go below this threshold, and then this will switch off. But once you switch off, the temperature gets higher, and then this voltage will be higher than this voltage, so it will command the air condition to turn on again. So you can see that around the reference here, that there will be any fluctuation in the room temperature will make this goes on and off. So you might hear the contactor or the actuator of the air condition going on and off, on and off, on and off, okay, around the room temperature, the set point. So this is very bad. I'm going to explain next time and continue from this point. So next time I'm going to finish this quickly, and then we'll do some solved problems similar to the final exam. Okay. Any question?
Hello, can you hear me?
Yes, yes.
Did you say that our what was it for the lab, the exam, was that going to be next Tuesday, or is it on the schedule?
For the electronics, for the theory, like this class exam is going to be, the final exam will be on Thursday. Okay, from 9:30 to 11:30.
Oh no,
for the lab.
For the lab.
Yeah, for the lab is going to be on Monday, on Tuesday.
Monday.
Sorry.
Okay.
Next
Tuesday.
Tuesday. Next Tuesday,
Okay.
yeah. 2 to 4.
Okay.
I'm going to give you just a circuit you build in multisim, and you find some results, and we discuss these results. Okay.
Okay.
So, do you have other exams during the same day?
For me, not that I know of.
Like, do you have like multiple exams in the same day for any of these 2 exams, or all of you don't have the? Like, do you have other exams on Tuesday or Thursday, next Tuesday and Thursday?
I think Thursday we just have a presentation for another class.
Okay.
For programming languages. that everybody has a reserved time?
Okay. Okay, we'll see. Like mainly on Tuesday, we need to have like enough time because 2 hours is not enough. Like because we need to like at least 5 or 10 minutes to discuss the results that you have shown. So we might need extra time a little bit, but I'll give you like maybe 1 hour to do the experiment, and the next hour we'll divide it into 5-10 minute sessions for one-on-one to discuss, you know, the results and understanding of the circuit. Okay, so we'll
Okay.
talk about this today, maybe in the lab. Okay.
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 Thank
Thank
you.
you so much, and see you in a few hours.